Hi everyone, welcome to this video. In this video, we will be discussing about Shannon-Fano coding. This is similar to the coding what we have discussed in our previous video, in one of our video called Huffman coding. So we use Huffman coding for data compression and communication. Same purpose, we use this Shannon-Fano coding as well. It's a coding where we can produce lossless data compression and we can assign code words to symbol based on their probabilities. So how frequently it is occurring, based on that we will be assigning code. Like Huffman code, Shannon-Fano code also will produce variable length code. Okay, and it is one of the earliest coding scheme in information theory, and it works by creating a prefix code. So we have already seen about prefix code. So what prefix code says is no code word is a prefix of another. Okay. And this Fanon coding will ensure efficiency and error-free decoding also. So it means once the coding is generated without any ambiguity, it can be decoded. For instance, if a sender is sending a message, and this message can be encoded using Shannon-Fano coding theory and can be transmitted, it can be decoded without any ambiguity, and then receiver will get the message. So how this entire process is achieved? So first the message will be scanned and the various symbols will be listed down and their probability of occurrence also will be listed down. Then the algorithm called Shannon-Fano will be applied. So this is how the Shannon-Fano algorithm works. There are 4 steps. If we go through all the steps, we will come to know how exactly that algorithm functionality will be there. Now, there is a small example given. We will go through this particular instance when we go through all these 4 steps. And later, we will go and solve our problem as well. So when you go with this, let's go what exactly Shannon-Fano will do at first. So we need to arrange all the symbols of the source alphabet in non-increasing order. So put all the symbols frequency in decreasing order or the probability in decreasing order. You have to think that there are totally 1, 2, 3, 4, 5, 6 symbols were there. Namely, you can consider any A, B, C, D, E, F, something like that. So there were 6 symbols and their probability is also listed. So we need to list these symbols in decreasing order. Okay, that's the first step. And then in the second step, we need to divide this list into 2 parts. In a point where 2 parts have approximately the same overall probability. So we need to divide this part in such a way that either you're getting an equal probability or nearest one. The difference should be less. Okay. For example, if you go with dividing the first two, you get a probability 0.5. The sum of these two probabilities 0.5. And then in the second part, also if you go for the summing probability, you'll again get 0.5. So you're getting exactly equal. It may not be always the same case. It might be different, but the difference should be very minimal. Okay. So that's the second step needs to be performed. And then the third one is after dividing, for the first half, we need to assign symbol 0, binary code 0. And for the second half, we need to assign symbol 1. And then repeat the same 2 and 3 steps until you can divide the given probabilities. And once you divided everything, then you will be deriving a code, and that is going to be your Shannon-Fano coding. So let's go and solve our problem. The same problem, I have written it here as well. Let's go and repeat these steps once again. So these are the symbols emitted by the source. Source has a message. In the message, these are the symbols emitted. And the frequency at which each symbol is emitted is also given here. The probability is given here. And both I have taken. Now we need to start performing. So I have did the first step, arranging them in non-increasing order. Then now we have to go and start dividing, assigning symbol, and we need to repeat it until multiple steps. Fine. Now, when we go and see this example. Like if you go for dividing equally, so if you consider the first two probability, it might sum to 0.55. And then the remaining is 0.45. It's not equal, but there is a difference. That difference must be small. Maybe if you are considering first three and then the remaining three, and if you sum up this probability, you might end up getting 0.7 and 0.35. But the difference between these two division when compared to this division is little high. So we don't consider this, we will go with this division. So let me go for first stage division. So I'll make division here. And once I divide, what should I do? I need to assign 0 for the first part, higher part, and 1 for the bottom part. Okay, so this is 0 and 0. And here 1, 1, 1, 1. Like this, you have to assign a binary bit for all the symbols. Next. So we have done step 3. What is step 4? Repeat 2, 1, 3 until you can divide the parts. Now, let's go and do the division for the first part. Can we divide it? Yes, we have totally 2 symbols. Let's divide it at this equal. Now, after dividing, what we have to do? We have to assign binary digit. So 0 for the higher part, 1 for the bottom part. Okay, that is done. Now, do the same thing for this particular part as well. So how can we exactly divide? Maybe this first part gives me 27, and then the second part gives me 0.18. First part is 0.27, second part is 0.18. So that is going to be the approximate division we can take. So I can divide it here. So when I divide it here, the top part will be getting the bit 0, 0, and the bottom parts will be getting the bit 1, 1. Repeat the same again. So if you go here, we have already divided. So we have just got the single symbol. So there is no more division needed for the first two. But here, if you see that you have two symbols, this has to be divided. So we will just divide it. For top, assign 0, for bottom, assign 1. Same, this division also can be divided. This part also can be divided, 0 and 1. Now, if you go on again, repeat 2 and 3, there is no more because we have got individual symbols. Now we can just go and produce the code words. For symbol A, the code word produced is 0 and 0. So we can use 0, 0 for representing symbol A. And for representing symbol B, you can go and use 0, 1 code word, 1, 0, 0, 1, 0, 1, 1, 1, 0, triple 1. And if you want, you can even mention the length of the code word, 3, 3, 3. So this is the code word produced by Shannon-Fano coding algorithm. And for A, what is the code generated? Code word generated is 0, 0, 0, 0, 0, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, triple 1. So these are the code words generated. And this is our code for compressing the message generated by the sender, and that gets compressed here and then sent to the destination. So that's how the Shannon-Fano coding will work. See, both are doing the same thing. The Huffman coding and the Shannon coding both are doing the same thing called data compression, and which we can use it during communication so that we can reduce the communication cost and time. But the difference between them is like Huffman coding is considered as more efficient algorithm when compared to the Shannon coding. Okay, there is one research paper. Let me just flash that research paper and we will see the difference. So there was one research done by few people. And if you see here, they have taken symbols. All the 26 alphabets, English alphabets they have taken. And then they are considering some probability of occurrence of these symbols in a message. And they have developed both Shannon-Fano coding as well as Huffman coding. Obviously, both are two different techniques. Huffman coding is generated using greedy method, and this is kind of a top-down approach is followed here. And at the end of the day, the research, they got these codes generated. And if you go and see the average code length, what was generated using Shannon-Fano coding, the average code word length generated is 4.16. And what is achieved using Huffman coding was 4.15. So you may not find the difference when you're going with less number of symbols. If you're going and having higher number of symbols, then you will feel the difference like this. And that's why Huffman coding is more optimal when compared to Shannon-Fano coding. Thank you.